While most of the world is focused on Tesla's flashy Cybertruck or humanoid robots, a quieter revolution may already be underway, one that could end lithium batteries as we know them. Leaks suggest Tesla has been developing a radical new power source: aluminum-ion batteries, faster, safer, and cheaper than anything in production today. And the first car to feature this tech might not be a luxury roadster, but the ultra-affordable Model 2. But how does this chemistry work? Why is Tesla's version different? And what does it mean for the future of EVs? The chemistry shift. For more than a decade, lithium-ion has been the beating heart of every Tesla vehicle. It powered the original Roadster, it made the Model S a global icon, and it remains the standard inside the Model Y, the world's best-selling EV. But lithium-ion technology, for all its success, has always carried three burdens: cost, safety, and scarcity. Now, with leaks pointing toward aluminum-ion, Tesla may be on the verge of trading those burdens for a completely new set of advantages. To understand why this shift matters, we need to look closely at what makes aluminum-ion so different. At its core, the difference lies in chemistry. Lithium ions carry a single positive charge, Li, while aluminum ions carry a triple charge, Ul cubed. This higher charge density means that for every aluminum ion that moves during a charge or discharge cycle, 3 electrons are transferred instead of just 1. The result is more efficient energy transfer, higher current density, and the potential for far greater output from the same physical volume of material. In simple terms, aluminum ions can do more work with less space. That efficiency translates directly into performance. Theoretical calculations suggest aluminum-ion anodes could deliver specific capacities up to 2,980 mAh per gram. Compare that to graphite anodes in lithium-ion batteries, which average around 370 mAh per gram. That's nearly a tenfold leap in potential capacity. For electric vehicles, this means longer range from smaller packs, or faster acceleration without needing oversized batteries. Behind performance. But aluminum-ion's advantages don't stop at performance. One of the biggest problems with lithium-ion is its reliance on scarce and problematic minerals like cobalt, nickel, and manganese. Cobalt alone has seen wild price swings, from $30,000 to $80,000 per metric ton, driven by geopolitical instability and the fact that much of it is mined in the Democratic Republic of Congo under ethically questionable conditions. Aluminum, by contrast, is cheap, abundant, and widely distributed. It trades for roughly $2,200 per metric ton and is mined in over 40 countries, with China, India, and Australia leading production. Recycling aluminum is also incredibly efficient, requiring only 5% of the energy it takes to extract it from raw ore. Then we come to the aspect of safety. Much as they might be engineered, lithium-ion batteries are exposed to threats emanating from thermal runaways. Under duress, they can heat up and explode, ignite, or very rarely, catch fire. Aluminum-ion designs employ ionic liquid electrolytes that are non-volatile and stable below 200 degrees Celsius. They are chemically stable, meaning they will not react violently when damaged. In tests at Stanford University, aluminum-ion cells have been crushed, punctured, and shorted without igniting. Even under extreme abuse, they remained cool. For the driver, this means no more worrying, no viral videos of EVs on fire, no fire during the charging process. Charging speed and durability. Charging speed may be the most newsworthy feature of aluminum-ion batteries. Tesla's current lithium-ion superchargers max out at 250 kilowatts, capable of delivering an 80% charge in about 20 to 40 minutes. Aluminum-ion prototypes have exceeded charging rates of 1,000 kilowatts for small cells, achieving full charges in under 3 minutes. When applied to EV packs, this means charging a family car in 5 minutes or less, which is comparable to filling a gas tank. It would be the last of the psychology barriers for millions of doubting would-be buyers. Durability at last. Lithium-ion batteries typically begin a detectable decline in performance after 1,000 to 3,000 charge cycles. By contrast, Batteries of the aluminum-ion type with advanced carbon nanostructure cathode constructions have demonstrated stability beyond 12,000 cycles at constant capacity loss. This would translate into over 2 million kilometers of driving, more than most vehicles will ever last. In effect, it could mean that an electric vehicle battery might outlive the vehicle itself. Together, these facts explain why aluminum-ion is being hailed as a possible lithium slayer. Increased capacity, faster charging, safer chemistry, cheaper materials, and much greater longevity. Every box in the EV industry's wishlist is checked. What makes Tesla's aluminum-ion unique? If aluminum-ion batteries already seem revolutionary, Tesla's rumored version takes the concept further. Leaks suggest Tesla isn't using an off-the-shelf design but a custom-engineered system built to dominate the next battery era. One breakthrough is self-healing electrodes. Lithium-ion batteries degrade as electrodes expand and contract during charge cycles, forming microscopic cracks that reduce capacity. Tesla's aluminum-ion reportedly uses silicon or aluminum hybrids with polymer coatings that realign at the atomic level. Tiny fractures close automatically, maintaining over 95% of original capacity after thousands of deep cycles versus the 20 to 30% loss typical in lithium-ion. With lifespans exceeding 15,000 cycles, these batteries could last decades. The cell structure also changes. Instead of rigid cylindrical cells like the 2170 or 4680, Tesla appears to be shifting to pouch-style soft packs. Laminated multilayer casings replace heavy metal cylinders, making cells thinner, lighter, and more flexible. Early reports say up to 30% lighter and as slim as 4 mm. This opens new engineering possibilities: flat stacking under the floor, wrapping around interior panels, or integration into seat bases and door frames. For a compact vehicle like the Model 2, pouch cells maximize interior space. Safety is a priority. The batteries that Tesla is supposed to be developing are said to be ionic liquid electrolyte-based. This would mean non-volatile, low-pressure materials that do not swell, combust, or rupture. This, coupled with pouch cells, reduces the need for heavy casings, thereby improving energy density and safety. More energy in liters, with less weight wasted. Tesla has imagined recycling again. Current lithium-ion recycling depends on energy-demanding smelting or chemical baths that create waste in the process and are expensive. On its aluminum-ion roadmap, Tesla envisions a closed-loop dry process based on vibration, pressure, and magnetic separation, recovering metals without producing any toxic byproducts, and bringing down recycling costs by 40%. Sustainability is thus built in as an advantage. As volume grows, economics will take care of themselves. On the strategic front, avoiding lithium, cobalt, and nickel frees Tesla from vulnerable global supply chains. Lithium prices undergo extreme changes, and cobalt is produced in unstable areas. Aluminum, in contrast, is abundant, mined in over 40 countries, infinitely recyclable, and is cheap when compared to lithium. This transition may ensure Tesla's qualification for U.S. federal incentives extended under the Inflation Reduction Act, which tilts toward sourcing materials domestically or from allied nations. The owners of the aluminum-ion-powered Model 2 could potentially claim tax credits of up to $7,500, establishing a significant market opportunity for Tesla. By creating self-healing electrodes, flexible pouch configurations, secure electrolytes, clean recycling processes, and strong supply chains, Tesla intends to provide an aluminum-ion battery beyond just another battery. Rather, it seeks to create a supportive ecosystem that encompasses durability, efficiency,